Good afternoon, everyone. So, do you have any questions before we start? Okay. In our last lecture, we started on first law of thermodynamics for open systems, and we left at this point explaining what's coming into system, exiting our system, and how it looks on a first law of thermodynamics. For open systems is called control volume, right? And we started with a closed system, which was control mass, right? Mass was trapped in our boundaries, in our system. But in this case, for an open system applications, mass is allowed through the boundaries. So my mass may change, may not. It depends on the process and the system itself. It depends on the question, right? It doesn't have to change, but it may. Okay? And we have also defined work into two categories: work in the form of shaft and work in the boundary work, right? Because of mass is passing through the boundaries and putting on an extra work on the system. Okay? All right, so today we will continue, we will finish this, and we will solve some problems. We will see a couple of applications on open systems. Okay. Okay. This is, we can also rewrite that. Qn plus work shaft on plus mass entering in the system. You may see this as an enter or in, or you can see as an outlet or exit. Okay? Hn plus kinetic energy plus potential energy. This is entering to my system. It's on the system. Minus Q out minus work shaft by minus summation of mass leaving my system, enthalpy out, kinetic energy out, and potential energy out. And all of these equals energy stored in my system or energy accumulated in the system. And this is the general version of the first law of thermodynamics. We will break this down into simpler cases, but it's a general form. Me breaking down into simpler form doesn't mean that you can always use those, right? Be careful when you use special cases, okay? Special case for steady state. Does anybody remember what steady state means? Yes.
There's no interruptions in the flow.
Right, correct. But in this equation, when we talk about steady state, okay, accumulation in the system is zero. D over dt basically zero. So there is no change per time. Okay? Knowing that, Q minus shock summation of mass parentheses the enthalpy plus kinetic energy plus potential energy minus mass leaving my system out, kinetic energy out plus potential energy out equals zero. So all parameters remain constant with time. Therefore, the accumulation is zero. Or,
excuse me, Professor. We can't see the notes. Thank you.
you mute yourself. Okay. Or Q minus workshop Q plus summation of all the inlets, and Hn kinetic energy N plus potential energy N equals workshop plus summation of outlets. H out, kinetic energy out plus potential energy out. Okay. All I did, take the minus terms or exits on the right hand side. For people on Zoom, this is what we did. Sorry for that. So, okay. We will go one step further for simplification and assume that one inlet, one outlet case. As I said, be careful when you use simplified versions. Special case, steady state, the one inlet, one outlet. The mass flow in one inlet must equal mass flow in the one outlet. So we may divide by the mass, because mass is equal on both sides. Okay? Mass flow rate as U dot over M dot plus H in plus kinetic energy N plus potential energy N equal to work dot shaft over M dot plus H out plus kinetic energy out plus potential energy out. That call M dot over M dot is Q, lowercase q, and work shaft M dot is small letter work shaft. And our equation, if you rearrange this, equation above, what we have for one inlet, one outlet, steady state, Q minus work shaft will be equal to enthalpy difference plus kinetic energy difference plus potential energy difference. Okay. Let's see how we apply this on real life applications. Okay, applications of the first law for open systems. First one we are going to cover is nozzles and diffusers. We should be done with nozzles and diffusers today. Second will be turbines. Third one will be compressors, pumps, and fans. Fourth one, throttles. And fifth one will be heat exchangers. Okay. Nozzles and diffusers are pressure increasing or decreasing devices. Turbines work producing devices. Compressors, pumps, and fans are work consuming devices. So work will be negative on those devices, or work will be positive on turbines, okay, to produce work. And throttles is pressure exchanger, or pressure valve. We will talk about in details. And heat exchangers. And heat exchangers are of this class. We cannot go into details, but we will only look at from a thermodynamic point of view. It's a completely different class, heat exchangers. Okay? Nozzles and diffusers. With one inlet, one outlet. One inlet, one outlet, and for diffuser, one inlet, one outlet. Nozzles, first one on the left is nozzle. The second one is diffuser on the right. Okay. Nozzle is also known as a speed increasing, velocity increasing devices or pressure decreasing devices. Okay. For diffusers, on the other hand, it's a pressure increasing or velocity decreasing devices. Right? If you write this simplified equation, first order equation for open systems, for one inlet, one outlet, steady state, right? Q minus work shaft equals enthalpy difference, kinetic energy difference, plus potential energy difference. Okay. Unless you are told or you are stated, it is stated in the problem statement specifically. I'm talking about general usual case in the nozzles and diffusers. Yes. Q is usually 0 because they are designed that way. Okay? But it doesn't mean that Q is actually 0. It may be specified in the problem statement that you have this Q. Okay? But usually the real or the main purpose is Q is 0 because you want efficient nozzle and diffuser or efficient device, I would say. Okay? So Q is 0, there is no shaft in diffusers and nozzles. Okay? And potential energy difference is negligible. Okay? What was potential energy? Elevation difference, right? Inlet and outlet. Between inlet and outlet. If you look at the elevation difference, right? Exit, H, or Z exit, the inlet will be negligible. Okay, if we take this down for nozzle, left-hand side will be 0, right-hand side, what I have is enthalpy and kinetic energy. It's also same for diffusers. Okay. Only difference between these two. Kinetic energy difference from state 1 to state 2 for nozzle is positive. It's negative for diffuser. Okay. Because velocity decreases on the diffuser, velocity increases on the nozzle.
What are you saying on the nozzle on the left? Under the two, what did that say? Or you have the other? On the right side. Yeah.
This one? Z sub E.
C7.
Correct. Meaning that elevation at the exit. Example. Again, we will be using tables again, right? Everything is same. And as I said in the previous lecture, open system that we started last week is general form. It includes closed system as well. Okay? You can break that general first law of thermodynamics equation for closed system. You can break it down for a closed system. Okay? Steam enters a nozzle at 30 bar and 320 Celsius and leaves at 15 bar with a velocity of 535 meters per second. The mass flow rate is 8,000 kilograms per hour, neglecting inlet velocity and considering adiabatic flow. We are asked to determine the exit enthalpy in kilojoules per kilogram, B, the exit temperature, Celsius, and C, the nozzle exit area in centimeters square. All right, we have a nozzle with one inlet, one outlet. This is my boundary on which I will be working on. I'm interested in that boundary. Okay, so with the one inlet, we can call it one, exit from 1 to 2. Okay? And this equation Q minus work shaft equals enthalpy difference from state 1 to state 2 plus kinetic energy difference from state 1 to state 2 plus potential energy difference from state 1 to state 2, right? For one inlet, one outlet, steady state open system derives. Right? What I know is mass flow rate, 8,000 kilograms per hour. Pressure at the inlet is 30 bar. Temperature is 320 Celsius, right? And velocity at the inlet is negligible, is zero, you can say. And at the outlet, pressure is 15 bar, and velocity is 535 meters per second. If you tell me what my enthalpy at the inlet by using your table, or you can check after I give you what the value is, will be useful for you. At the inlet, H1 is 3,043.4 kilojoules per kilogram. Q is 0 because it's adiabatic. It is stated specifically as adiabatic. Work shaft, 0, because there's no shaft in a nozzle and diffusers. Potential energy is negligible. So if I write my first law of thermodynamics for an open system for one inlet, one outlet, steady state, enthalpy difference or kinetic energy difference will be equal to 0. And this is what I like. And H2 from here, H2 minus H1 plus V2 squared over 2 will be equal to 0. Right? Because V1 is 0, right? Velocity at the inlet is 0. From here, H2 equals H1 minus V velocity at the outlet squared over 2. H2 will be, I know my H1, I just read it from the table, 3,043.4 joules per kilogram minus velocity at the outlet is given 545 meters per second squared over 2, 1 kilojoules per kilogram over 1,000 meters squared over second squared. I need to get the same unit vector. From here, H2 will be equal to 2,900.3 kilojoules per kilogram. If you check table A2, the H we just found, 2,900.3 kilojoules per kilogram, exceeding our saturated vapor volume property, which puts us in a superheated region, right? So now we need to go to the superheated table and find our outlet temperature, internal energy at the outlet, entropy at the outlet, and etc. Okay? So what I need for this, so exit is superheated. Right? T2, if we check that enthalpy value at 15 bar superheated region, okay, what you have, temperature lies between 240 Celsius and 280 Celsius, okay, which means that you need to interpolate, okay? So 240 plus 280 minus 240, 2,900.3 minus 2,899.3, 2,992.7 minus 2,899.3. This should give you T2 as 240.4 Celsius. I can also find my specific volume at the outlet, which I will be using for calculating my outside exit area from using my continuity equation. Mass flow rate at the inlet should be equal to mass flow rate at the outlet. Right? Here, specific volume will be 0.1483 plus parentheses 0.1627 minus 0.1483 2,903 minus 2,899.3 over 2,992.7 minus 2,899.3. Specific volume from here at the outlet will be 0.1485 meters cubed per kilogram. Mass flow rate at inlet equal to mass flow rate at the outlet. I know that, right? They must be equal. But from here, I also know how to find my flow rate. If I know my specific volume, area, and velocity, right? Which I do. Only thing I don't know is area. Now I can calculate that. Area will be equal to mass flow rate times specific volume over velocity at the outlet. Mass flow rate given as 8,000 kilogram per hour. Specific volume, we just calculated 0.1485 meters cubed per kilogram. And I need to convert this hour a second, 1 hour, 3,600 seconds. And centimeter to meter, because I'm asked to find the area in centimeters. And velocity at the outlet is 535 meters per second. Area from here will be 6.16 centimeters squared.
Where on the
Centimeter over meter. Because you want area. Right? You have m square, you have m meter square. It cancels out. Any questions? Okay, let's solve another problem. And a diabetic diffuser is employed to reduce the velocity of an air stream from 250 meters per second to 40 meters per second. The inlet conditions are 0.1 megapascal and 400 Celsius. Determine the required outlet area in centimeters square if the mass flow rate is 7 kilograms per second and the outlet pressure is 0.12 megapascal. In this example, we have diffuser. So basically, they are the same thing. But as I said, diffuser is a velocity decreasing device or pressure increasing device. So in this case, it is used to decrease the velocity from 250 meters per second to 40 meters per second. Okay? And I know my inlet pressure and exit pressure. I know my flow rate. From there, I should be able to find my properties from this data, right? Okay. Diffuser. This is my diffuser with one inlet, one outlet. from 1 to 2. Net outlet. What I know from the problem is velocity at the inlet is 250 meters per second. Pressure at the inlet is 0.1 megapascal. Temperature 400 Celsius. And mass flow rate is 7 kilograms per second. And at the outlet, velocity 40 meters per second. Pressure is 0.12 megapascal. And we're asked to calculate area. I don't need the area. But I know mass flow rate inlet must be equal to mass flow rate delta. And I also know my flow rate can be found from velocity, right? Area and specific volume. And this should be equal to mass flow rate at the inlet. Now, from first law of thermodynamics, for one inlet, one outlet, that is 8 open system device, Q as work shaft equals enthalpy difference plus kinetic energy difference plus potential energy difference. And there is an equation of state is used to find the properties of an ideal gas, right? I have an ideal gas in this case. So I can use EVRT because I have an air in the system. Potential energy difference can be neglected. Enthalpy difference can be calculated because nothing is specified in the problem statement. We will be using constant specificity. Okay. So CP can be found. We can find the CP from the table by knowing the temperatures, right? We take the average temperature for air table and find the specific, constant specific heat, the constant pressure, to find enthalpy difference. So I should be fine everything. The elevation difference between inlet and outlet is negligible. It's negligible. It's very small. You can include it, but it will not make any difference. For diffuser, U is 0. Work shaft 0. And as we said, potential energy difference equals 0. which gives us enthalpy difference from state 1 to state 2 will be equal to minus kinetic energy difference from state 1 to state 2. Which is 1 minus 1 over 2 40 meters per second square minus 250 meters per second. It's my kinetic energy difference from state 1 to state 2. Okay. I need a unit conversion because I have meters square over second square. I need kilojoules per kilogram. 1 kilojoules per kilogram equals 1,000 meters square over second square. So enthalpy difference from state 1 to state 2 will be 30.45 kilojoules per kilogram. Okay. Okay. There's a little bit of trick here. Listen carefully. Okay. So I just found my enthalpy difference between state 1 and state 2. And since I'm going to use a constant specific heat model, right, which is CP in this case, if you go ahead and check your tables for an ideal gas air table, what you will see is CP doesn't change dramatically, say, as a function of temperature. Okay? So it is around 1.04, 1.05 with a couple hundred temperature increase or decrease. Okay? The change in the CP or CV is really small. Okay? If you check your table. Right? Okay. So now I can find my enthalpy at the inlet, H1, right? It should be around 607, or I might be wrong. Okay? So knowing that, I know my CP doesn't change too much as a function of temperature, but in order for me to find my CP or read from the table, I need my second temperature, which I don't know, right? And I will do reverse processing, trial and error by using the CP being constant, almost. Clear? Okay. So I'm going to estimate around 700 Kelvin as my T average. Okay. If I do that, temperature difference from state 1 to state 2 will be equal to enthalpy difference from state 1 to state 2 over CP. And CP at that temperature will be 1.075 kilojoules per kilogram Kelvin. Okay, and I know my enthalpy difference. Just found it, 30.45 kilojoules per kilogram. Here I can find my temperature difference as 28.33 Kelvin. here T2 will be what? T1 plus 28.33 Kelvin. It will be 701 Kelvin. My estimation was pretty close. In engineering, sometimes you will have to do this kind of try and error because two components that you have depend on each other. Temperature increases, Cp increases. If Cp decreases, temperature decreases. Sometimes you need to pick one of them to get other one. Okay? This is what we did here. By using, as I said, knowing as a fact that Cp does not change dramatically as a function of temperature. All right? Okay. Now I can find my other properties, which I only need one specific volume to find my area of the outlet. Okay, specific volume case will be RT2 over T2, R 0.287 kilojoules per kilogram Kelvin times temperature 701.33 Kelvin over 120 kilopascal. It will give me 1.67 meter cube per kilogram. Area at the outlet will be equal to mass flow rate at the outlet times velocity times specific volume at the outlet divided by the velocity at the outlet. Mass flow rate 7 kilogram per second. Specific volume is 1.67 meter cube per kilogram. And velocity is 40 meter per second. Which gives us 0.29 meters squared. Right, that I am asked to find in centimeter square. So A2 will be meter squared times 100 centimeters over meter. So it will be equal to 2,900 centimeters squared. Questions? Let's solve one more problem. Nitrogen gas enters an insulated nozzle at 200 kilopascal with negligible velocity. At the exit of the nozzle, the state of the fluid is 120 kilopascal and 27 Celsius. And the exit area is 10 centimeters square. The mass flow rate is given as 0.2 kilograms per second. Determine the exit velocity in meter per second and the change in temperature in degrees Celsius. Nozzle with one inlet, one outlet. The boundary over my open system device. And I have nitrogen entering and leaving my system. At state one, you can call 1 or 2. I know my flow rate is 0.2 kilograms per second. Velocity, outlet at inlet is almost 0, it's negligible velocity. And outlet pressure 120 kilopascal. Temperature 27 Celsius or 300 Kelvin. Area to outlet is 10 centimeters. From continuity, M1 equals M2. Area inlet times velocity at inlet equals divided by specific volume at inlet equals velocity at outlet, area at outlet divided by the specific volume at outlet. And I also know my first law of thermodynamics for an open system with a one inlet, one outlet at a steady state, Q minus workshop equals enthalpy difference from state 1 to state 2 plus kinetic energy difference from state 1 to state 2 plus potential energy difference from state 1 to state 2. And I also know the equation of state for an ideal gas, PV equals RT. Potential energy difference is negligible. Yes, alpha T. Enthalpy difference equals Cp times temperature difference from state 1 to state 2. Right? Okay. I know my pressure. I can find my universal gas constant, and I know my temperature. So I should be able to find my specific volume here, right? So specific volume at the outlet, the R times T2 over P2, right? R, what is my R? So how do I find my R?
Gas constant.
From table? No, you should be able to calculate.
Gas constant divided by the molar mass.
Correct. Universal gas constant over the molar weight, right? Universal gas constant is constant for every single I will get, but molecular weight is not, it's identical. So we should be able to find the gas constant for a particular ideal gas, right? So let's look. 8.314 kilojoules per kilogram Kelvin over, that was a nitrogen, the 28 kilogram per kilomole. So this is kilomole, 8.314 kilojoules per kilomole Kelvin. Okay. Times temperature, 300 Kelvin, over the pressure is 120 kilopascal. The specific volume from here will be 0.742 meter cube per kilo. Velocity, the outlet, mass flow rate, right? Mass flow rate is given as 0.2 kilogram per second times specific volume over area. 0.2 kilogram per second times the specific volume, the outlet, meter cube per kilogram, over the area, 10 centimeters squared. Okay? But I need to convert this to meters squared to trying to get rid of this. Right, 1 meter fills 100 centimeter in square. What I have is meter per second. Velocity will be 148 meters per second. Okay. Okay. Q minus work shaft equals enthalpy difference plus kinetic energy difference, right? Plus potential energy difference. This is 0. This is 0. This is 0. And the velocity at inlet in this is 0. And I can also break this down into Cp times delta T from 1 to 2. Okay. And velocity 1 equals to 0 here. T2 minus T1 will be equal to minus velocity 2 square over 2 Cp. Okay. Kinetic energy difference equals enthalpy difference. equals minus 148 meter per second squared over 2 times 1.039 kilojoules to kilogram Kelvin. And to convert this kilojoules per kilogram, 1000 meter second squared. The temperature difference delta T from state 1 to state 2 will be minus 10.6 Kelvin or minus 10.6 Celsius. Please make sure you go over these examples and try to figure out what I've been doing. Okay? Try to solve it by yourself. I'm going to write an extra problem, and I want you to work on it when you have a chance. And next class, when we come on Thursday, I will give you the solution of that. Okay? Any questions so far? Yes.
Why is
Because you have a summation, subtraction here, right? Cancels out. So it doesn't matter. Example. Steam enters an adiabatic diffuser as saturated vapor at 110 Celsius with a velocity of 220 meters per second. At the exit, the pressure and the temperature are 1.5 bar and 120 Celsius, respectively. The exit area is 50 centimeters square. Determine A exit velocity in meter per second and B mass flow rate in kilogram per second. You have a diffuser with one inlet, one outlet. Okay. We don't have time to solve this, but as I said, if you work on it, I will start solving this problem next class. Okay. We have a steam flow net up. This is all for today. If you have any questions, I will be here. And you can also email me. Have a good one, everyone.